So we can calculate the mass percent composition from a chemical formula. The other way to do it is, oh, I'm sorry, jumped ahead. You can also calculate a chemical formula from the mass percent composition. That's going to give us the empirical formula, not the molecular formula. And the way this is done is you would take the compound and you'd figure out what mass of compound did I start with, and then you break it down chemically into the individual elements and measure the mass of the elements. And from that you can figure out what the chemical formula is. The word empirical just means derived from or guided by experience or experiment. So this means it's a formula that's found by experiment. The empirical formula has the lowest ratio of subscripts. So it gives us the smallest whole number ratio of each type of atom in a compound. It does not necessarily tell us how many atoms of each element are in a molecule. The molecular formula is always going to be a whole number multiple of the empirical formula. It might be the empirical formula multiplied by 1, or it could be 2 or 3 or 4 or 17. So an example is hydrogen peroxide. So the chemical formula for hydrogen peroxide is H2O2. So one molecule of hydrogen peroxide is going to look something like this. So you're going to have 2 oxygens and 2 hydrogens. That's one molecule. Okay? That's the molecular formula. It gives you the formula of the actual molecule. Is this the lowest ratio of hydrogen atoms to oxygen atoms? No. It's like a fraction. Ratios are really similar to fractions. So this would be a fraction of 2 over 2. That can be simplified to 1 over 1. So this is the molecular formula. The empirical formula is HO. Because it's the lowest ratio, 1 to 1. We get this molecular formula by multiplying this one by 2. It's a whole number multiple. Any questions? Empirical formula is like a reduced fraction.
What if it was like 3 to 2?
Like a ratio of 3 to 2?
Yeah.
So like if you had Fe2O3. So the ratio there is 2 to 3. That's like a fraction, 2/3. That can't be reduced. So it's already in its lowest form. So there, the empirical formula and the molecular formula would be the same. Water's like that. So water's H2O. 1 oxygen atom, 2 hydrogen atoms. The ratio is 2 to 1. That can't be simplified or reduced. So the molecular formula and the empirical formula are the same. Any other questions? So sample of water is decomposed and produces 3 grams of hydrogen and 24 grams of oxygen. And this is a picture of how you might do that. You can actually do it just with a 9-volt battery. You've got 2 leads in here, and the electric current flowing through here decomposes the water into hydrogen and oxygen gas. And here we're collecting that in these inverted test tubes. And it's not a coincidence that the hydrogen gas has twice the volume of the oxygen gas. We'll talk about that in another chapter. So how could we figure out an empirical formula from the data? We have the mass of oxygen and we have the mass of hydrogen. The formula gives us the lowest ratio of numbers of atoms of each, right? So we could take this 3 grams of hydrogen and calculate how many atoms of hydrogen are in there. It's going to be a crazy huge number, right? Because it's going to involve Avogadro's number. Or instead of calculating the number of atoms, we could calculate how many moles of atoms, and then we're going to have more reasonable numbers. So the approach here is we're going to take the mass of the element and figure out how many moles of that element. And we're going to do that with the other one too. Find the moles of oxygen, and then we're going to find the ratio of the moles, and that's going to give us the subscripts for the formula. So here's the instructions. Obtaining an empirical formula from experimental data. Start with the mass of each element. That's going to be given to you. Convert each mass to moles using the molar mass of the element as a conversion factor. Divide all the moles by the smallest so that you get ratios that are 1 or larger. We don't want to make more fractions. If the moles are not whole, if the mole ratios, it should be, if the mole ratios are not whole numbers, multiply all the moles to get whole numbers. We'll look at what that means, and then write the formula using the numbers of moles as subscripts. So sometimes you'll end up with this ratio, and it won't be like 2 to 1. It'll be like 1.5 to 1. And we can't just round it off. We need to do something to get it to be whole numbers. So these are the fractional subscripts that you might end up encountering. So if you get 0.5 and you multiply that by 2, then you're going to get a whole number. So if this makes sense to you, that's awesome. If it doesn't, I have another way. So let's do this. Here's that problem. We've got 3 grams of hydrogen, 24 grams of oxygen. We're supposed to find the empirical formula. So we're going to write down the masses. So I've got 3.0 grams of hydrogen, and I have 24 grams of oxygen. We need to go from mass into a unit that has to do with numbers of atoms, and the mole is the best one to use. So I want to convert this into moles of hydrogen, and I want to divide by grams of hydrogen down there. How much does 1 mole of hydrogen weigh? Oh, depending on what periodic table you look at, 1.008. So 3 divided by 1.008 equals 2.9. Strictly speaking with sig figs, that'd be the end of it. Carry 2 extras though. These problems, calculating empirical formulas, we're going to end up with whole numbers in the end. The significant figures are going to disappear. The important thing is to use enough. More digits is better when you're doing these problems. If you round things too much, it can mess up your answer. So that would be the number of moles of hydrogen. And so I need to do this for the oxygen as well. I want to figure out how many moles of oxygen. So I need to divide by grams of oxygen. 1 mole of oxygen, we look it up on the periodic table, weighs 16 grams. So I've got 24 divided by 16, and this is showing me 1.5. And that happened to be just an even number. It didn't have any extra digits after it. Moles of oxygen. It's supposed to have 2 sig figs anyway, so it's okay. So, in this sample of water, there were 2.976 moles of hydrogen for every 1.5 moles of oxygen. I need whole numbers because as a molecule, you can't have 2.976 atoms of hydrogen for every 1.5 atoms of oxygen. We have to get this to be whole numbers. So we're going to do a ratio. So we're going to divide both of these numbers by the same number so we keep the relationship the same. So I'm just going to look at these and say, well, which one's smaller? Well, the 1.5 is smaller. So I'm going to divide by 1.5 moles of oxygen. I'm going to divide by 1.5 moles of oxygen. Well, 1.5 moles of oxygen divided by 1.5 moles of oxygen is just 1. You're always going to end up with one of them that comes out to exactly 1. This one, I've got 2.976 divided by 1.5. And my calculator tells me 1.984. And if we're looking at the units there, that's moles of hydrogen per moles of oxygen. Is this a whole number? No. Is it really close to a whole number? Yeah, it is. The reason this doesn't come out exactly is because we started out with measured quantities of elements. And there was uncertainty in the measurements, and so that brings us some uncertainty here. So now the hard part is to know, well, is this close enough that I can round it or not? So here's my guideline. So Mrs. K says, if it's within 0.2 of a whole number, round it. So is this within 0.2 of a whole number? Yeah, it's actually within 0.02 of a whole number. So I can round this to 2. So that is very close to 2. That would be 2 moles of hydrogen per 1 mole of oxygen. This number becomes the subscript on hydrogen. This number becomes the subscript on oxygen. So these are my subscripts. So I have H2O. That's my formula.
So let's say it wasn't.
Yeah.
Right down.
We'll come to an example where it's not within 2 of a whole number, and then we have to do something. I didn't want to start with one of those, but we'll get one.
What was the reasoning behind choosing the 1.5 versus divided by the 2.96?
That's a good question. Why did we divide by 1.5 instead of this number? I want whole numbers, like 1, 2, 3, 4, 5. If I take 1.5 and divide by 2.976, I get 0.5054. Okay, so that is, I'm always going to end up with numbers less than 1 then, and what I want is numbers that are 1 or greater. So when I divide by the smallest, then my ratios are all 1 or larger, and it makes things easier. So just divide by the smallest. The hardest part of doing problems like this is remembering the steps. So any other questions? Let's do another example. Sample of a compound is decomposed in the laboratory and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula of the compound. So we need masses of each element that's given to us in the problem. We're going to convert the masses to moles, and then we're going to find the ratios of moles. So 165 grams of carbon. So I want to convert that to moles of carbon. So I need to divide by grams of carbon. 1 mole of carbon weighs 12.01 grams. I got that from the periodic table. So I take 165 divided by 12.01. 13. I should have 3 sig figs in this. 3.7. And so I want to make sure I carry along extras. So that many moles of carbon. The next one is 27.1 0.8 grams of hydrogen. And I want to find out how many moles of hydrogen that is. 1 mole of hydrogen weighs 1.008 grams. And so those units cancel out. 27.8, bless you, divided by 1.008 equals 27 point, this should also have 3 sig figs, so we don't want to round further than that. I'm going to carry 2 extra digits, that many moles of hydrogen. And then we've got oxygen, 220.2 grams of oxygen. Converting that to moles, (220.2) divided by 16, and this equals 13.7625 moles of oxygen. Any questions? Those are the sorts of calculations that you need to get proficient at. You shouldn't have to think about those too much, converting grams to moles. So now we see that these moles of carbon and moles of oxygen are really close to each other, right? And then we've got this 27.57. We need the ratio, though. So we're going to pick the smallest. We're going to pick this one because it's just a smidge smaller than that one. We're going to divide all of them by the smallest. So you can include the units in here, but it'll also work out if you leave the units out. So we usually don't show all the units in this step. So that first one, because it's divided by itself, that's 1. And then we've got 27.579 divided by 13.738 equals. So this comes up to be 2.0074. And then this one at the bottom, 13.7625 divided by 13.738 equals. This one comes out to 1.001. Actually, no, it's 1.7. Okay. So those are my ratios. I've got 1 and 2.0074 and 1.0017. These numbers are less than 0.2 away from a whole number. This is very close to 2, so I can round that to 2. And I can round this one to 1. This is the subscript for carbon. This is the subscript for hydrogen. And this is the subscript for oxygen. So it's going to be C1H2O1, but we don't usually write the ones. So we'll write that as CH2O. That's the empirical formula, the formula derived from experiment for that compound. Any questions? We got whole numbers in that one as well, which means we need another example. Ibuprofen. This is my answer to all of my children's ailments. My head hurts. Take some ibuprofen. I sprained my ankle. Take some ibuprofen. Ibuprofen, an aspirin substitute, has the mass percent composition. Carbon is 75.69%, hydrogen is 8.80%, and oxygen is 15.51%. Calculate the empirical formula of ibuprofen. Well, what we learned is we need masses of each element. They didn't give us masses of each element. They gave us percentages. Well, from a percentage, we could figure out a mass, but we need to know what the sample size is. The calculation is going to work out and come out to the same empirical formula no matter what size the sample is. It could be a metric ton, it could be 1 microgram. We just need to pick a sample size. I like to pick 100 grams because that makes things easy. 75.69% means 75.69 grams of carbon per 100 grams of sample. So if I just choose 100 grams, then the percentages are the same as the number of grams. So that's what I recommend that you do. Choose a 100 gram sample. So then 75.69% carbon turns into 75.69 grams of carbon in 100 grams. Right? And for hydrogen, 8.80% means 8.80 grams per 100 grams. So that's 8.80 grams of hydrogen. And then the oxygen is 15.51 grams of oxygen. Any questions about that? Forgetting how to do that would cause you to, start pulling your hair out during an exam. I'll just warn you about that one, that it definitely could be on an exam like that with a percent. Now we convert grams to moles. So I want to multiply by 1 mole of carbon over 12.01 grams of carbon. I do it like that so the units work out, and I'll get moles of carbon. 75.69 times 1 divided by 12.01. 6.302. My percentage and my molar mass had 4 sig figs, so I definitely don't want to go lower than that. And I'm going to put 2 extra digits in there just to be safe. So that's moles of carbon. For the hydrogen, I'm going to multiply by moles of hydrogen and divide by grams of hydrogen. 1 mole weighs 1.008 grams. So 8.8 divided by 1.008. So it's going to give me 8.7301 moles of hydrogen. And then for the oxygen, 1 mole of oxygen divided by 16.00 grams of oxygen. Again, we're just doing it so the units work out. 15.51 divided by 16. 0.9697375 moles of oxygen. Any questions? All those other ones came out to be larger than 1, but the oxygen came out less than 1. And so, that might make your brain say, wait a minute, did I do that right? Yeah, because this number is less than 16, so when I divide by 16, I should get something less than 1. It's okay. What do we do next? Divide by the smallest. So here, this is the smallest one. So I divide that one by itself, and I'm going to get 1. You'll always end up with one of them that's exactly 1. And then I'm going to divide this one by 0.969375. 8.7301 divided by 0.969375. When in doubt, write down more digits than you need, or than you think you need. And then this one, again, dividing by the same thing. I have to divide all of them by the same number because I want to end up with the same ratio. 6.302 to 8.73 to 0.969. That's just not a whole number ratio. We're just dividing to get these into whole numbers. Who's Amber, and why are they testing this over and over? Pardon me? No, they're just testing their system that doesn't ever seem to work when they need it to work. Okay, so that's for the carbon. Okay, so this one's exactly 1. Can I round this to 9? Yeah, that's within 0.2. How about this one? Can I round it to 7? No. Because this is 0.5 away from 7. This is almost exactly between 6 and 7. I can't round it. So this is where we need to multiply all of them to get whole numbers. So if you recognize that 0.5 is the fractional equivalent of 1/2, multiplying by 2 is going to get you a whole number. If you don't recognize that, the approach is multiply by 2. If that gives you a whole number, great. If not, try 3. If that doesn't work, try 4. If that doesn't work, try 5. You shouldn't have to go past that. So I'm going to try 2. So I'm going to take that 6.5013 and I'm going to multiply by 2 and see what I get. So when I multiply by 2, I get 13.0026. Oh, that is within 0.2 of a whole number. So for this one to be within 0.2 of 7, it would have to be between 6.8 and 7.2. So like 7.1 or 6.9, we could round, but this 6.5 we can't. Multiply that by 2, I have to multiply all the others. Was that your question? Yeah. So I can't just multiply one of them because we're looking at the ratio of carbon to hydrogen to oxygen. And we need to keep the ratio intact. So I'm going to multiply that one by 2, 9.0059 times 2. And that's going to give me 18.0118. Okay, that's still within 0.2 of a whole number. And I multiply by this one by 2. So this rounds to 13, and this rounds to 18, and this one's 2. So my formula, and we don't really need to think too hard about which element goes first. Just do them in the same order that the problem gave you, and it'll be right. So carbon, there's 13 carbons, and 18 hydrogens, and 2 oxygens. And those seem like large numbers for subscripts, but they're perfectly fine. There are molecules that have 1,000,000 carbon atoms. Any questions? Yes?
So you only multiply by 2 if the number doesn't round to a whole number?
Right. You only have to multiply these if you can't round these to whole numbers. If you did multiply when you didn't need to, what you'd find out is that this ratio would not be the lowest ratio, and then you'd end up dividing by the same number again. Any other questions? Yes?
Is the empirical formula that can't be simplified anymore?
Yeah, this cannot be simplified. A ratio of 13 to 18, there's no common factors. This is the lowest ratio. You'll always get the lowest ratio of subscripts doing it this way. Now, do we know if that's the molecular formula for ibuprofen? No, we have no way of telling from what information we're given in this problem. But that's the empirical formula. Any other questions? So let's do another one. A 1.56 gram sample of copper reacts with oxygen to form 1.95 grams of the metal oxide. What's the formula of the metal oxide? Well, calculating an empirical formula, what do we start with? The masses of elements, right? What are the 2 elements in this compound? Copper and oxygen. So we've got copper and we've got oxygen. What is the mass of copper? 1.56 grams. What's the mass of oxygen? Did they give it to us? No. This amount of copper reacts with oxygen to form 1.95 grams of the metal oxide. The whole compound weighs 1.95 grams. 1.56 grams of it is copper. How can we figure out the mass of the oxygen? Subtracting. So if we take the mass of the whole thing and we subtract the mass of the copper, we can find out the mass of the oxygen. So the mass of oxygen is 0.39. If we have a class of 20 kindergartners and 15 of them are boys, how many are girls? The rest of them, right? 20 minus 15, there must have been 5 girls. So that's our mass of oxygen. The rest of this is the same pattern. Convert the grams to moles. So here we have grams of copper. I'm going to multiply by 1 mole of copper and divide by the molar mass of copper. I can't quite remember right now. 63.55. Grams of copper cancel out. 1.56 divided by 63.55. 0.024547. And then I've got this mass of oxygen that I want to convert to moles of oxygen. So I multiply by moles and divide by grams. So the units come out, converting grams to moles. 1 mole of oxygen weighs 16.00 grams. So I've got 0.39 divided by 16. 0.024375. These numbers here are a lot smaller than the numbers we were seeing in previous problems. That's okay. This is just a smaller quantity that we're looking at, that's all. So that's my moles of copper and my moles of oxygen. I'm going to take the smallest and divide both of them. So this one, the moles of oxygen, is a little bit smaller. And so that's going to equal 1. And you can probably predict what this one's going to end up rounding to, but do the math anyway. 0.024547 divided by 0.024375 equals, so this comes out to 1.00705. Can we round that to 1? Yeah. It's within 0.2 of 1. So we'll call this 1. So this is the subscript for copper, and this is the subscript for oxygen. We don't write the subscripts in the formula, so this is just CuO. Any questions? So we've done actually 4 variations of this problem. You're given the masses, you do the calculation, all the numbers come out, you can round them to whole numbers. You're given a percentage. So you have to say, well, I'm going to pick a 100-gram sample so that my percentages can just be written as masses, and then you do the problem and you come out with numbers. Then we had that variation in there where you do that, but the numbers don't come out to be whole numbers, and you have to multiply them all. And then this is a different version where instead of just giving you the masses, we give you the mass of one of the elements, and we give you the mass of the whole compound to make you calculate the mass of the other element. So those are the variations that you're going to see. Questions? Oops.